Okay, so this is our last lesson for this little unit we've been doing on Gibbs free energy and entropy. So the learning intentions for today are to explain reaction spontaneity using terminology including Gibbs free energy, enthalpy, and entropy, and to solve problems using standard references and the Gibbs free energy formula to classify reactions as spontaneous or non-spontaneous. So we know how to calculate change in enthalpy and we know how to calculate change in entropy. So our delta H, change in enthalpy, is obviously the enthalpy of the products minus the enthalpy of the reactants. Similarly, our change in entropy, delta S, entropy of the products minus the entropy of the reactants. Now, if we calculate both of those for a particular reaction, we can plug it into the Gibbs free energy equation. We also take into consideration temperature when we do that. The answer to the Gibbs free energy equation is going to tell us whether a particular reaction that we have on paper will proceed as written. Will it be spontaneous or is it a non-spontaneous reaction? At the start of these lessons, we spoke about the fact that we could save ourselves a lot of time and trouble if we could apply a formula to determine whether a reaction will occur. And it's the Gibbs free energy formula that we are going to apply to determine whether we have a spontaneous or non-spontaneous reaction. Things to keep in mind before we go ahead as well. The universe likes to go from high energy to low energy. So our delta H, our change in enthalpy, tends to be negative, which is an exothermic reaction. And we know that exothermic reactions are more common because of that. The universe likes to go from high energy to low. We also find that the universe likes to go from a state of orderedness or low entropy to high entropy or chaos and disorder. So the delta S value, or our change in entropy, tends to be positive. So we have an increase in entropy, which is preferred, and a decrease in energy is preferred. Now, these signs here, a negative delta H and a positive delta S, whatever those signs happen to be when we calculate our change in enthalpy and our change in entropy respectively, we need to analyze those to determine whether a particular reaction will be spontaneous or not. And we'll do that using the Gibbs free energy equation. Okay, so here's our Gibbs free energy equation. The standard Gibbs free energy change, which is our delta G, which we're going to calculate, it's a measure of the net result, the energy, or enthalpy, and our entropy drives for a reaction. So we're going to calculate our delta H, enthalpy, and from that we will subtract the temperature in Kelvin multiplied by the change in entropy for a reaction that we calculated. And that Gibbs free energy change, delta G, it's going to tell us whether a reaction will occur or not. The free energy that we're talking about here, it's energy that's available to do work. So in other words, it's energy that will sustain a particular chemical reaction. We won't have to continually put energy into that reaction in order to keep it going. Spontaneous reactions release free energy as they proceed. So even though a particular reaction may need a kickstart to get going, the fact that it releases energy sustains that chemical reaction, and we'd call that a spontaneous reaction. A spontaneous reaction, therefore, is going to have a negative delta G value. That negative delta G value indicates it's releasing energy, which can be used to sustain itself, and that's a spontaneous reaction. If we have a delta G less than 0, we have a spontaneous reaction. If it's greater than 0, so a positive value, we have a non-spontaneous reaction. So we'll have a look at a couple of types of reactions here, or a few types of reactions, and we'll classify them as spontaneous or not, and then looking at that, we'll actually come up with a better definition of what spontaneous is. Type 1 reactions occur as soon as the reactants are mixed. By the sounds of that, that's going to be spontaneous. Type 2 reactions require initial heating. We have to light a match to, burn a piece of paper. Despite that initial heating, it's going to release heat and sustain itself. So we'd call that a spontaneous reaction. Type 3 reactions occur only if we continuously apply energy and heat them to get them to completion. That would be non-spontaneous. And obviously, if the reaction doesn't occur at all, that's going to be non-spontaneous as well. So our definition that we want to get down here for a spontaneous reaction is one that occurs without any ongoing input of energy. Despite this type 2 requiring a bit of an initial kick to get going, we'd still classify that as spontaneous because we don't have to keep applying any energy for it to go to completion or for it to continue. So that would be spontaneous. So here's our definition, our more specific definition of what a spontaneous reaction is. And obviously the converse of that, a non-spontaneous reaction, is one that doesn't occur or requires ongoing input of energy or heat. So before we plug any values into our Gibbs free energy equation and do a couple of examples, we'll just have a look at what different changes in enthalpy, different changes in entropy for a particular reaction, what influence they're going to have on our delta G value, and then how we're going to interpret our change in Gibbs free energy as well. So how to interpret this delta G value. We'll also have a look at the role temperature is going to play in some of these reactions as well. So to start with, if both of the energy and entropy drives are in the forward direction in a particular reaction, so we have an exothermic reaction, a negative delta H, and we have an increase in entropy, so we have an increase in disorder and chaos, and we have a positive delta S, the reaction goes as written, and delta G will be negative. If we have a delta G that is negative, we have a spontaneous reaction, and remember that negative delta G is indicating that it's releasing free energy that's available to sustain that particular reaction. If we have the opposite and we have a positive delta G value, it means that it's going to be absorbing energy and we're going to have to continually apply heat or energy to that particular reaction to sustain it. Negative delta G is a spontaneous reaction. So let's look at the opposite here. If both drives are in the reverse direction, so we've got an endothermic reaction or a positive delta H, and we have a negative delta S, so we're creating order. The reaction is not going to go as written, and delta G will be positive. So let's have a look at those two scenarios in this table above. First scenario we looked at here was an exothermic reaction creating disorder. The universe is completely happy with that. We're releasing energy and we're creating chaos. So that's always going to result in a spontaneous reaction or a negative delta G value. The opposite we just looked at then was if we had an endothermic reaction creating order, it will never be negative. Our delta G will never be negative in that case, and it won't go. So what we can say here is that if delta G is negative, then under standard conditions, the reaction proceeds in the forward direction at that particular temperature. If delta G is positive, the reaction goes in the reverse direction. A spontaneous reaction will therefore have a negative delta G value. Non-spontaneous reactions will have a positive delta G value. Now there's a couple of things to keep in mind here with regards to temperature. There's two scenarios here. Let's have a look at the table. What if we had an endothermic reaction that was creating disorder? What happens in that particular case? We can see in the final column of that table it says that the delta G value will be negative. In other words, the reaction will proceed as written if we raise the temperature or if the temperature is high enough. And here's an example of that particular scenario. We have solid water, we have ice, we know that it melts at 273 degrees Kelvin. Below that temperature, that reaction will proceed in the reverse direction. We will have liquid going to a solid state. But if we raise the temperature and we get to 273 Kelvin, or the melting point, then we've raised the temperature high enough in order for that reaction, going from a solid to a liquid, to start to proceed. Okay, so in that case, temperature, which is part of our Gibbs free energy equation, comes into play. So in that particular case, if we raise the temperature high enough, an endothermic reaction that creates disorder will proceed in the direction written. The opposite would happen here if we had a negative delta H. So we've got an exothermic reaction, which is good, so to speak, but it's creating order. Well, the opposite would happen to the one we just spoke about then. If we had a lower temperature, so if we lowered the magnitude of this temperature here, we would end up eventually getting a negative delta G value, and in that case, the reaction would proceed as written. So the take-home message from this is, A negative delta G value is going to result in a spontaneous reaction. It's releasing energy that will sustain itself. A positive delta G value will not go ahead as written, but temperature can play a role in determining whether some of these reactions will actually go as written. Do we have to raise the temperature in one particular instance, as the case is with melting ice, solid to a liquid? Or do we need to lower the temperature, which is the case here with an exothermic reaction that is creating order? All right, so let's put it all together. Let's calculate our change in enthalpy, our change in entropy, and plug it into our Gibbs free energy equation and try and predict whether or not this reaction will go as written under standard conditions at this temperature, which is 298 Kelvin. So we've got calcium hydroxide solid producing calcium oxide solid and water vapor. We're going to use the heat of formation values from the table and our entropy values from the other table. We're going to plug those into our three equations and see if we can determine whether this reaction will go as written. So let's start with our change in enthalpy. So we have calcium hydroxide, and we need to get our heat of formation, which is minus 987. What else do we have? We have calcium oxide, and that is minus 636. So again, we're looking at these values at the top here in this top table. And we've got water vapor. Make sure you get the gas, not the liquid. So H2O gas, we have minus 242. Okay, so now we need to do our change in enthalpy. So this is going to be sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. So let's go ahead and put in negative 636 plus our water vapor, which is minus 242, minus the enthalpy of the reactants, which is calcium hydroxide, so that'll be negative 987. Our delta H value, therefore, is going to be plus 109 kilojoules per mole. All right, so we have an endothermic reaction. Okay, to start with, good. So now that we've done our calculation for change in enthalpy, let's use the table and get our entropy values. So let's work out delta S. Remember, working out delta S, very similar to enthalpy. We take the sum of the entropies of the products, and from that we minus the sum of the entropies of the reactants. So we've got calcium hydroxide, and that has entropy of solid 83. And we have calcium oxide, entropy there 38. And water vapor, H2O gas, entropy 189. So you can see the entropy value for a gas there much higher than the entropies of these solids here. Okay, so that makes sense. Now, let's work out our delta S. Delta S is going to equal the sum of the entropies of the products, and from that we'll minus the sum of the entropies of the reactants. So let's start with 38, calcium oxide, plus our water vapor, which is 189, so that's our products, minus the entropy of our reactants, so 83, and our delta S. Our change in entropy, therefore, is plus 144 joules per Kelvin per mole. Now, what we can do here is actually, because we need to get everything into kilojoules, we're going to change our joules here, 144 into kilojoules, so divide by 1,000, we're going to have, let's just convert that now, 0.145 kilojoules per Kelvin per mole. All right, we'll just get our units all sorted, make sure everything's the same. Okay, so we have a plus value for our delta S. Plus 144 joules or plus 0.144 kilojoules. So if it's a plus value, we've just increased the amount of entropy. Okay, so that's our value there for change in entropy. So we have an endothermic reaction that is creating disorder. Let's plug that into our Gibbs free energy equation. So we have delta G is going to be equal to our delta H minus the temperature multiplied by the change in entropy. So let's plug that in. We have delta G is equal to, let's go back over here, what have we got? 109, which is our change in H, minus 298 Kelvin, which was specified in the question, minus 298 multiplied by our 0.144. Remember, we just changed the units, so everything's standard. 0.144 kilojoules per Kelvin per mole, and we can calculate our delta G. Our change in Gibbs free energy is going to be plus 66 kilojoules per mole. Interesting. So we have a plus value here for our Gibbs free energy. Remember, anything above 0, if it's a positive value, under these conditions, this reaction at the top here, that's not going to proceed as written. So we can say here, at this temperature, the reaction goes in reverse direction. At this temperature, the reaction goes in reverse direction because we have a positive delta G value. This reaction under these conditions won't go as written. So we've worked out our delta H, and we've worked out that it was an endothermic reaction. Positive delta H value. We did create disorder. We have a positive delta S, but at this temperature, it wasn't sufficient to get this reaction going as written. That's how we'd work out Gibbs free energy and interpret it. There's obviously multiple steps you'll have to go through, calculating your enthalpy, calculating your entropy, plugging all of that into your Gibbs free energy, then finally interpreting under these conditions whether this reaction is spontaneous or not. And in this case, it's not. So we're going to do the same again. You might want to pause it here and go ahead and try this problem and then come back to the video and see how you've gone. So again, we need to calculate delta H, delta S, and plug that into our Gibbs free energy. We're going to use 298 Kelvin again, so we're using the standard temperature here. We've got our table so we can get our values for entropy and heat of formation, and we're going to predict whether the reaction will go as written or not. So like we've done previously, we're going to start with our delta H. So we have 2 SO2. So we have to be aware here that we're using the coefficients here. So we've got 2 moles of SO2 and we have 2 moles of sulfur trioxide as well. So our delta H, we need to do our 2 moles of sulfur trioxide. So we're going to have 2 times SO3 is 396. Minus the enthalpy of our reactants. So we've got 2 moles of negative 297 for our sulfur dioxide. We don't have to worry about oxygen because it's an element, so we don't have to worry about the heat of formation in that case. So let's plug in those values. So our delta H, what's it looking like so far? We have negative 792 minus negative 594. Delta H equals minus 198 kilojoules per mole. So we have an exothermic reaction. We've got a negative delta H value. Let's go ahead and do our change in entropy. So again, we do the sum of the entropies of our products minus the sum of the entropies of our reactants. So we're going to have a delta S. It's going to be equal to 2 times, and then we're looking at SO3 here, 2 times 257 minus, and we will do entropy for our oxygen, so we've got minus 205. We need to do the sum of our reactants, 205 plus 2 moles of sulfur dioxide, 2 times 248. So our change in entropy is looking like 514 minus, yeah, that's 701. Change in entropy is going to be minus 187. Let's divide by 1,000 though and convert this to kilojoules so we can plug it into our Gibbs free energy equation. We're going to have 0.187 negative 0.187 kilojoules per Kelvin per mole. All right, so we have a negative delta S. So we have a decrease in entropy. Okay, so we've got a negative delta H, which is good, so to speak. We've got an exothermic, but we're creating order here. So we have to work out at this temperature if this is going to proceed or not. All right, so let's use our delta G. So I'll just write it over here. So our delta G, our Gibbs free energy, change in Gibbs free energy is going to be our delta H minus the temperature multiplied by our change in entropy. Okay, so I might just start over here. We have our delta G is therefore going to be negative 198, our exothermic reaction, negative delta H, minus 298 Kelvin, which was specified, multiplied by our negative 0.187 kilojoules per Kelvin per mole. Delta G, change in Gibbs free energy, is negative 142 kilojoules per mole. All right, we have a negative delta G value after all of that. So what does that negative tell us? If it's a negative delta G value, it means that the reaction proceeds as written and it's a spontaneous reaction. So we can say that this reaction goes as written at this temperature. So it's a spontaneous reaction that will sustain itself. It's releasing free energy, and that free energy is available to keep that reaction occurring. So that is entropy and Gibbs free energy. I hope that's given you guys a little bit of help in trying to understand that. I know my videos are not the clearest sometimes, but hopefully that's gone some way to helping you work out a few of these problems. Feel free to email me or get in touch if you need clarification. More than happy to help. Best of luck, guys, and hopefully see you soon.